Excellent. Welcome. Thanks for everybody being here. We got some new people here. Hi, Donna. Okay. So it's the obligatory slide, asking questions about anything. I have all the answers. If you have any questions about your presentation, team presentation next Thursday, let me know. If you have any questions about the field trip to the Magical Bridge Playground, that's next Tuesday during class time. So that's going to be a ton of fun. You're going to have, I guarantee you will have more fun next Tuesday than you've ever had at Stanford in a class. So you don't want to miss it, okay? Okay, we got the normal set of sign-up sheets. A couple more things about these hints and suggestions about team projects. Most important is that you send your PowerPoint slides to me without any embedded videos. If you have a video that you want to show, put it up on YouTube and send me the link, and have the link in your slide so we can run it from there. Alternatively, you can put the whole thing on Google Drive or whatever and send me the link that I can access it here during class, because we're not going to have any students present from their laptop. It just makes it a lot quicker to do it all on one laptop. These are things I said last time. Basically, what you really want to do is practice. The more you practice, the better your presentation will be. And I can tell the teams that are practiced, and I can tell the teams that haven't practiced. So you do a much better job when you practice. So please do that. You want to practice for timing. You want to know where to stand when you're presenting. You want to know where you stand when you're not presenting. So try to get all that stuff worked out. It just makes for a better presentation overall. You're going to be using this slide presenter, and basically number 1 is the laser pointer, and number 2 is the advanced slides. So that makes it real easy for you. Okay. Well, everybody has done this. So this was the sign-up sheet for the presentation order. We got that all taken care of, it looks like. And for the final presentation, the order will be reversed. So 9 will be number 1, and so on. So I hope that works well for everybody. So field trip on Tuesday. Everybody is invited to attend because it's a big open space, and that includes people from the community. You can be there as well. And if you can, you're welcome to carpool students there. We need some more cars to make sure we get everybody there. This is what it looks like. Here's Olenka. You'll be seeing this stuff in person. It's really neat. So we went there last year, and it's required that you get me on the merry-go-round and spin me around as fast as you can, okay, and see if I survive. But for you, what you have to do is balance on this rotating disc, okay? You have to see how many G's you can pull over here. You have to experience sliding down where there's no slide on the grass, and swinging in this special swing. So you're going to have a great time, lots of smiles. Okay, so I want to thank people who have signed up to carpool next Tuesday. Their names are listed here, along with the number of passengers that it can take. And we still need some more carpool drivers. So there's space for people to sign up as carpool drivers down here. Just put your name, cell phone, make and model of the car, and so on. So what we're going to do is people who have signed up to carpool will bring their cars around on Santa Teresa on the curb, along the side there, and wait for the students that have signed up to carpool with you to get in the car, and we'll head out. Okay? So drivers, be there promptly at 4:30. Students, be here promptly at 4:30. So the sooner we can get everybody there and get everybody to the playground, the sooner you'll have fun, okay? And as far as leaving early, if people have to leave early, that shouldn't be a problem, because what's going to happen is we're going to hear from Helenka for maybe 20 minutes, and then I'll send you off to check all the equipment's accessibility and stuff. And as you're doing that, you're going to be turning from students into kids. I guarantee that. So whenever you're done with that playground experience, you're welcome to leave, okay? Even if it's early. But like last year, it was like almost dark before the last person left. So here's the sign-up sheet again. On the top, you'll see drivers who sign up to carpool, and at the bottom, there's empty spaces for people to put their name in for driving and passengering, okay? So I'm going to pass this around. Make sure it gets to everybody. Okay. So here's directions. Here's the printed directions, which I'll also send you over the weekend. But basically, it's near the intersection of Middlefield and Charleston. Okay, so that's in Palo Alto. And I'll show you how to get there. So we're here, and so you just go out on Embarcadero, make a right turn on Middlefield, and almost at Charleston, you'll make a right. And so as I was flying over, I took this picture. So here's Middlefield here. You want to make a right turn just beyond Adobe Creek. And then you're going to be parking in this area down here and walking into the Magical Bridge Playground along the tennis courts. I think I have a better slide of that. So this is what it looks like when you're driving. Here's Adobe Creek, and you make a right turn here, and there may be a sign on this fence here. So you make a turn here, go all the way down to the end by these trees, and that'll be where you park. So park all the way down here. And here's a blown up view of where you park, where you turn in, the tennis courts, and so just make your way. There should be a entrance in the fence over here. Just walk over here and walk down this pathway to this part of it. I mean, it'll pretty obvious when you get there. Okay, I'll send this to everybody. So today we have Peter Axelson, who came all the way from Nevada today, an out-of-state guest presenter. After his talk, there's a bunch of us. By tradition, we get together at the Max's Opera Cafe in Stanford Shopping Center. Typically, there's Peter and I and his guests and some people from the community that attend. But if you're a student and want to attend, that would be great. I can pay for Peter and one of his guests, but that's about it. So you're on your own, but this would be a great experience for you to talk a little bit more with Peter. So everybody knows where Max's Opera Cafe is in Stanford Shopping Center. It's toward the north end of the shopping center. And they have really good corned beef and pastrami. Okay, well, they have to know that. Next time I'll have a little discussion on vintage assistive technology, but I wanted to give Peter as much time as possible, so I'm going to save that for next time. But I do want to talk about something that came up on Tuesday, this web content accessibility guidelines. And these guidelines are basically a document, a standard for web content accessibility for people with disabilities, a variety of disabilities. And basically what it does is it's how to do it, how to make your web content more accessible. And it's been shown that having your content accessible means you'll have a wider market for stuff. There's lots of people with disabilities and older adults who are on the internet, and you just want to make sure they have access to the information. And so they have lots of examples on how to make things accessible. Any questions about that? Yes.
Where's the best place to get started finding out about?
Go to the World Wide Web Consortium, W3C. Just enter those 4 letters in, and you'll find it, and they have all sorts of explanations from top to bottom. Okay. So we'll take our break now. If you haven't done so, sign in, meet with Dave, pick up your evaluation forms, keep that carpool thing passed around, and we'll be back in about 5 minutes. Sorry? Let's just strap it in there. Yeah.
I'll have my head turned this way. So.
Oh, yeah, that's good.
Hi, how are you doing?
Peter and I are old friends because we're both old. I think I met him the first year I was out here in 79, 80. Peter was a student here at Stanford. He's a graduate of Stanford Mechanical Engineering. Peter is a rehab engineer who sustained his spinal cord injury in 1975 while in the Air Force Academy. He began applying engineering and design principles to overcome his daily living hurdles. In 1981, he founded his company, Beneficial Designs. It's an engineering design firm dedicated to designing, developing, testing assistive technology. He'll be talking all about this. His major accomplishments include developing the first chairlift compatible mono-ski with a shock absorber, working to establish wheelchair testing standards, improving seating systems for wheelchairs, and creating a system for assessing trails that will improve access to outdoor trails for people of all abilities. Peter is the founder of his company and director of research and development. He spends a lot of his time traveling throughout the world and to Stanford University, attending meetings and presenting his work. And he's also a pilot. He has an adapted plane and an avid monoskier. So let's welcome Peter.
All right. Thank you, everyone, for coming in today. I know you're already all into your projects and getting ready to give presentations on them and stuff. And working on projects here at Stanford was one of my favorite things to do. So I'm going to share projects that I've been working on for the past 30 years. And I'm going to show a lot of images of examples of things that I've worked on. And I'm looking forward to sharing all this stuff with you, but I just want to share that we have a website at Beneficial Designs. www.wheelchairtestcenter.com, and our mission statement is basically we believe that all people have the right to participate equally in all different aspects of life through your design of daily living activities and equipment to do work and to study and to participate fully in life activity, whether it's leisure or recreation or study or self-care, whatever somebody's needs are. And I think I already said all of that. So I just want to point out that I work with a team of people. So all the stuff you're seeing is that all these different people that help me and work with me to do these different things that I do. It's pretty hard to accomplish things if you just work by yourself. So we have a lot of young people that are students. We get students from high school that are wanting experience working in my office. My daughter comes in and helps in the office. And we get them involved in what we're doing, and so it's a whole spectrum of ages and skills and abilities. We have people that work with us all over the world. Our machinist works like the graveyard shift. He likes to work at night, and he's a night person. We got a guy that runs our wheelchair test lab. We do a lot of wheelchair testing. This guy's a mechanical engineering student at University of Nevada, Reno. This guy's a GIS student at University of Reno. He's a computer software student. Our graphic artist lives in United Emirates, and he does all our map making from there. We have a GIS that was a mom that came back to work with us again. So she has a son with a disability. Our electrical engineer lives in Germany in the winter, comes back to Montana in the summers. This guy's a retired math teacher, and he does assessments of sidewalks. And another designer guy that does assessments of sidewalks. This guy's a rancher, helps me do all the amusement park work that we do for Universal Studios and Disney. And then we got to have tools and stuff to work with. So you're all got access to the shops here. We have our own little shop with drill presses and milling machines and bead blasters and powder coating oven, and we've got everything we need to do, got a little milling 4-axis mill that we can use to make stuff. And it's all inside an airplane hangar now, so that makes it really fun and interesting for me. That's my aircraft that I usually fly down here in. And it would have been a really, really, really beautiful day to fly down, but I brought down this 300-pound powered wheelchair for a friend of Dave and mine that needs a powered wheelchair to get around now. So I couldn't possibly fit that wheelchair into the aircraft and still take off. So we drove down. We've got devices that I'm going to explain further, and this is our new design area next to the hangar where we work. And first I'm just going to show you some of the pieces of how we test wheelchairs. We're one of 2 wheelchair test labs in the US, and I helped write all the test procedures for testing wheelchairs, so I know them kind of inside and out. And so we like to bash, break, and mutilate wheelchairs. So this is just a static test on an armrest, trying to see how strong it is in the downward direction. And we also do impact tests with the 25-kilogram pendulum into the footrest and caster and stuff. Then we put it on a machine. It's a machine that's driven by a motor. The slats go around and hit the wheels and jostles the wheelchair around. It's got a very heavy test dummy inside of it. It's got to go 200,000 cycles on those drums and survive. And we also use powered wheelchairs, and the powered wheelchair actually drives the drums to test itself for the same number of cycles. And we have a drop machine. We also pick it up and drop it on. So there's a lot of the powered wheelchairs have 6 wheels now. They have a center drive wheels and pivot wheels out in the front and the back. This is the drop machine. That's the most brutal test, probably 7,000 drops. We calibrate the test dummy, just tipping it, measuring the balance angle forward and backward, get the center of mass located exactly where it should be for that size dummy. We test everything from the simplest manual wheelchair to these heavy-duty track chairs that will climb out in the woods to allow people to go hunting and stuff like that. We test wheelchairs in their most crazy configuration they can possibly go into. This is a tilt and space seating system. So if somebody needs to do pressure relief, they can tip way back in the chair to unweight their bottom to let the blood flow. And so we see what angle it tips over in every orientation. It can be adjusted to, and there we are testing in the hangar up in the top picture there on our big test ramp and our small test ramp. So that's the ramp that we use. We crank it up and we drive the chair down full speed and we throw the brakes on. We try to see if we can flip it over by throwing the brakes on, throwing it into reverse, turning the power off, whatever way we can to try to flip it over forward, backward, sideways. And it makes a big mess when it flips over and the weights go flying everywhere. But that's our job, is to, if we can make them fall over, then we figure out how to adjust the center of mass or change the design a little bit or change the suspension on the chair. This is one that happened to fall over there. It ran into this curb full speed and flipped over backwards and made a big mess. So basically the design work that we do, though, so we'll turn testing aside for a minute. I'm going to talk about some different kinds of product development that we do. We also do assessment of products and assessment of environments for accessibility. And I'm a big advocate of universal design and designing products so they can be used by a broad as possible range of user groups as possible. People that are missing vision or hearing or sensation or mobility or hand function. And we work on mainstream products. We see a lot of opportunity to make mainstream products more accessible with universal design. And then I'm going to talk mostly, though, about adaptive products, which would I call like designing something that's specific to a certain need or user group. Then I'm going to talk about personal technologies and activity-specific technologies. Personal technologies would be like my glasses that I wear, the things that you wear that you use for everything you do. My wheelchair, this would be part of my personal technology to let me move and live. Artificial leg would be a personal technology. And then I'm going to talk about activity-specific technologies, to something that allows you to do a certain thing that you want to go out and try to do. So, first of all, one thing that happens when somebody has a disability as a result of an injury or something is that their life radically changes. Suddenly, everything's different, and you're trying to figure out, well, how do I continue doing the physical things that are important to me, and the intellectual things and the spiritual things that are important to that person. And some people are born with the disability, so they may not have balance right from the beginning because they're not able to experience things physically like maybe they should or that they want to, or they can't be able to do things. So I'm always getting out there with my daughter, doing crazy things out over the Snake River here, or rafting. She loves to go rafting, so we had to figure out a way that Dad could go rafting. And it's mostly getting to the raft is the hard part. Or fly fishing up in the Sierra Mountains. Or, she decided she wanted to go on a zip line. Okay, so let's figure that out. A couple harnesses later, and experimentation, and off we go. And so tree to tree to tree to top, six trees. I survived 6 trees. My daughter's like, can we go do the Grande now, Dad? And it's like, maybe next year. So there's that physical dimension. There's also what I call like a sociological dimension, which would be, some people like to do things independently. Some people like to do things like real closely with another person, where they're dependent on another person, like maybe when you go rock climbing together with somebody and you have to really trust that other person. And then there's most things are like require a lot of interdependence that you do with other people. And this guy wanted to try out my hiking chair. He was quad, came to a spot where he couldn't get through, so he had to rely on some help to get through. This guy on the bottom here is a ventilator dependent quadriplegic, breathing with a supplied air ventilator. So he had to design this ventilator system to run off a little scuba tank so that he could get a continuous flow ventilator so he could go skydiving. And his wheelchair with the ventilator is waiting on the ground somewhere. And so I'll tell you about the story at dinner. It was pretty interesting. So this is an ultralight aircraft. So I worked with a group to design some hand controls so we could fly aircraft. So now I'm going to talk to you about 3 different kinds of technologies: the personal, the activity-specific, and the environmental. First, I'm going to talk about the activity-specific technologies. This is my student project here at Stanford. I designed the first sit ski. So I built this little sled to try to figure out, well, some guys drug me out of the hill and said, we want you to test this little Norwegian sled and give us your feedback. I'm like, okay, I'm not sure I want to ski. I was a really good skier before my injury. I don't think I want to ski. And that was my motto. I didn't want to do things that I used to do because I just thought I'd get frustrated trying to do what I used to do. So they talked me into testing this little sled. It was like going down the hill on a lunch tray. It went about as fast sideways as it did forward. But I said, it was fun. I was like, I think I can figure out a way to make this work better. So I started designing the first sit ski. And I just still remember the design review, sitting in one of these rooms here in Turbin, which got torn down, and all the professors saying, who's going to want to do anything like this? And I was like, I don't know, maybe just me. And so it turned out I'm wrong, because now it's all a Paralympic sport. So that evolved into working on monoskis. This is the first monoski with a shock absorber under there, and molded seating and a latch mechanism so I could latch and get up on the ski lift. So I got to race on the U.S. Disabled Ski Team, and now I still teach adaptive ski instructors. So skiing is a big part of my life, and still a big part of my life. This is a bi-ski on the right. All you have to do is tilt that, and the skis mechanically tilt back and forth to steer. And it has to be able to go on the lift. If you can't get on the lift, you can't go up the mountain. So it has a latch mechanism to slide up on the lift, and the skis drop down out of the way, and then it comes back down off the lift with the instructors in this case. Underneath my jacket, I don't have any back muscles, so if I lean forward, I just fall forward if I don't have my hands out. So I rigged up this fishing rod, this fiberglass fishing rod, and I wear a harness on my back with a tubing with a couple of Delrin lifesavers in it, and the rod slides in and out of there. So whichever way I flex, that spring rod helps spring me back up. So I've got the stomach muscles to pull forward, but I don't have the muscles to go back up. So that helps me in a variety of different things that I try to do. This is my articulating cross-country ski that I use. It's flexed forward and then back. So when I go forward, I can reach further forward with my poles, and it stretches the bungee cords in there. And then when I pull through, those bungee cords snap back, so it kind of gives me a little kick and glide. So I get an increased range of motion, and bottom line is it's more efficient, it's faster. This is a backcountry ski I designed. It's got individually adjustable outriggers on the side, so if I'm on a cross slope, I don't fall over in the cross-country ski, which usually has 2 skis. So that's another device. This is the PaxBack, which I'm wearing on the back of my wheelchair here. It's an adjustable back support, so with this strap I can tighten it up. So I tighten it up when I came in here. If I'm going downhill, I'll loosen it so I can lean back more so I don't lose my balance going downhill. This is Peter's pneumatic panel pedal pusher. It's a beach ball bellows pump with a blood pressure cuff that you pump up to take somebody's blood pressure, and a little pump. So I strap that over my stomach, and by tightening my stomach muscles, it pushes the sostenido pedal on the piano. So it's a mechanical way to use your stomach muscles to work the piano pedal. I wanted to drive a car with a stick shift. So most hand controls are all for vehicles with automatics. So brake is always push, and then gas is either rotate or twist like a motorcycle or pull or something. So this one I set it up with twist for throttle, push for brake, and down for clutch. So I could be on a hill and I could have the brakes in, the clutch in, and put the gas on and slip the clutch out and let off the brake just with one hand. And so we couldn't find anybody to manufacture this. It's kind of a high liability thing. So we put the plans for this on our website, and people write, and they sign a release, and we send them the plans. And quite a few people have built these hand controls. This is a dynamic seat, like a sort of a balance chair, if you've ever heard of that concept where you sit against your knees. So I made a chair that I could sit that way in the office, and I made a wheelchair that I could sit that way with the pressure on the front of my shins and then also tipped way forward. So it has several postures for sitting in. This is my hiking shoes. So when you're in a wheelchair, you have to have a different wheelchair, essentially it's a different set of shoes for each thing you try to do. So you have a racquetball sports chair, a tennis chair, hiking chair, whatever, whatever you go to do. So this is a hiking chair, and it has four-wheel disc brakes, these little discs there. So it can actually drive down a flight of stairs in control. And I'm up on a rock here, and this is up on Yellowstone Park with the geysers out there in the distance. Hand bikes. This was a project that I supervised and mentored at the design or smart product design program, or product design program? I can't remember. Mechanical engineering program. And the students worked on creating a way to pedal a two-wheel bike that would lean like a real bicycle, but when you stop, you can put down these little casters. So you can start out with the casters, pull the casters up, and then lean like you would on a regular bicycle. And Doug Schwann, they've probably met Doug Schwann, yeah. So this is the tandem version of this, and Doug's brother manufactured these bikes so that they were available. This is a molded contoured seat. That's a seat cushion, and this is the front, and this is the back, and these are my ischial tuberosities right there, and my greater trochanter on the right and the left. So that's the shape of the seat cushion that I carved for my aircraft when I fly to give me good connection to the aircraft in a molded contoured seat. So pressure reduction requires the seat cushion to sort of accommodate people's shape to reduce that pressure. And so we designed what we call the Skelly. It's a skeleton embedded in gel to be able to test the seat cushions. So we would put the gel and load it in with a crank it down and measure the force we're pushing it in with. And then we would measure the pressures. So we can measure these pressures using a map, which you'll learn about over at the Palo Alto VA Rehab Center. They use this map for measuring people's sitting pressures. So the higher the colors go, the higher the pressures are. Red is bad, blue is good, green, yellow, orange, as the pressures get higher. So basically you can see like sitting on foam or sitting on different kinds of cushions. This is, you can see the lowest pressures, that's sitting on a Roho air cushion versus sitting on, something that's just foam. So different cushions work for different people, and no one cushion is best for everybody. So we made an adjustable skeleton so we could put an obliquity in there or a pelvic tilt or a twist, because we wanted to be able to simulate different conditions. So if we used our mechanical butt, we could put it on there and get those pressures, and then if we simulated the obliquity, you can see how the pressures all show up on one side. And then if we did a posterior pelvic tilt, the pressures all end up on the sacral tailbone there. And so we can simulate those different things. We were also very interested in, a lot of people have a lot of spasticity, and when you're at the VA, maybe you'll see some people that you'll see their feet kicking around, or they'll have a spasm and they'll kind of kick them back in their chair. And so those extensor spasms tend to throw people out of their wheelchairs. Their hips, their body tries to straighten out, and their hips literally try to just jump out of the chair. And so there's different ways to strap people in to prevent that, but what we wanted to do was come up with a way to accommodate the spasm and then bring them back into position. So we designed a seating system that had rubber bungees there and a little flexible spring rod there that would let the pelvis move back and forth in the chair with some control. So this was kind of what the prototype looked like, and then this is what the final product looked like. So it straps onto the seat rails, and then there's a pelvic belt around the person's pelvis, and allows people to do different kinds of things. And this gal is a dancer with the Axis Dance Group in Berkeley, and she uses the hip grip for being able to do these dance moves and then come back up into position again. And of course, we always test things. So whatever it is you're doing, think of how you can simulate, using it a million times or whatever usage it's going to see. So in this case, we hooked it up to a motor and just with this rod right here, and the motor goes round and round and round, and the rod just makes it go back and forth. Test this thing a million cycles back and forth to make sure it's not going to fail. We also look for functional tests that we can do. A real simple one we did is putting a tripod behind a wheelchair, and we measure how far the user can reach without falling over. So we'll measure that, with the seating intervention and without the seating intervention, so that we can see, did we increase that person's functional reach? Or you might want to look at their functional reach to the side. So like, can this person reach down further to the side with or without the intervention that we're designing? So, and this is a system that's manufactured by a wheelchair seat manufacturer. So another thing I wanted to do was pushing on the wheelchair hand rims. They're really slippery and they're hard to grab and hard to move. And it's also really rigidly mounted to the chair. So I wanted to create something that was more like wearing a pair of tennis shoes versus a pair of street shoes. And so we mounted the hand rim, the metal part, to the wheel rim with a layer of thin, flexible urethane rubber. And that's what's on my chair here. And the advantages is that this thin layer of rubber, when we tested lots of different shapes of it, creates a place that you can push on to get a grip. So now I don't have to grip real hard around here. I can just push really good right there to get the traction I need to push. So I don't have to actually grip the hand rim at all. I just move my hand and push on the hand rim because that rubber is that urethane is really grippy. So we measured we had to figure out how to measure the grip. So we put our thermometer on there with a standard amount of weight sitting on the top, and then measured the torque to turn the wheel to see what the friction was between the hand and the hand rim and the thumb. So we always think of objective ways to measure whatever it is that you're trying to test. So the same thing with the impact absorption. We figured out a way to impact it with an impact and measure what's going on. So we did a fatigue test on the hand rim, push, 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 and then so we broke it. It took 444,000 cycles, so we figured that was pretty good, that we succeeded to make it last that long. So to do our research with that, we had to create an instrumented wheel. So we put a torque sensor in the hub on the wheel, and then we set this guy up, and we set up a wheelchair biomechanics lab. So we have the treadmill and the instrumented wheel and our subject that looks pretty geeked out there. So let me show you what we geeked him out with. We're measuring the respiration, so we can measure how much oxygen they're actually consuming. We're measuring their heart rate. We're measuring their grip with the EMG electrodes in the hand. We're measuring motion capture on their bodies, so we can create the moving stick figure on the computer. And we're measuring the push rim forces down at the wheel. So we can do all those things together to essentially do. There's about 4 or 5 research papers and a PhD that came out of this project at Stanford. The student that did this project did get his thesis with Dr. Leifer here at Stanford. The grip rim is another grip type thing we designed, and it has a rubber sleeve with plastic pieces sliding on the hand rim. And so when you push on the hand rim, it actually squeezes against the hand rim inside. And so you can actually hold on to this part, and the hand rim's turning around inside, but then when you push on it, it grips it. So it's kind of a way to grip when you don't have grip. So somebody that's quad maybe just pushes on those and they can grip without physically gripping. So I like outdoor recreation water sports, and so I wanted a way to figure out how to get a better seat. I was always stuffing in life jackets and cutting boards and things inside the canoe to get a good seating system. So we wanted to design an adaptive seat. This is the seat that I use in my kayak, which is molded to me, but this is the product that we ended up designing as a result of the seating project we worked on that clamps into the canoe, and it has adjustable hip pads to hold the pelvis really solid, and then if somebody has a higher injury, it'll hold their torso in place for being able to paddle in a canoe. So again, this is a commercial product that's available through a company called Creating Ability, and they're selling these to adaptive paddling sports programs for people with disabilities. And again, we had to quantify objectively, so we set up a concept 2 ergometer with pulleys to create a paddling ergometer, essentially. So I'm rowing a concept 2 ergometer, and I'm wearing the expired gas meter, and I have a motor rocking the canoe back and forth while this is going on. And then I have a cadence software that we set up to kind of get my rowing stroke. So it's like my metronome for paddling. And so we're measuring the force of the paddling that I'm actually accomplishing paddling. And so we wrote a few papers with that, and there's one of our subjects in the system paddling away in there. And we also did a lateral balance test where we just tip the canoe and see how far they can tip. And so we're doing this with no adaptive seat. We're using like a Crazy Creek seat that might be available. And then we're using the new seat that we designed to show that we can increase function and performance and all these different things. So be on your things, the projects you guys are doing, think of how you can measure the increase in function and performance for the person that you're designing, whatever it is that you're working on. And then of course we had to make sure it was safe. So when you tip over in the water, you got to make sure you come out of the seat, because if the seat holds you in there really well, so well that you drown, that's not a successful seating system. So we did an actual test in the pool in the backyard. A lot of folks have been hurt, actually paralyzed from surfing accidents, hitting into the bottom of the sand. So we designed a way to modify a wave ski with a molded seat and straps across the knees to hold a support bar and straps to hold the legs. So you pull this one strap to sort of release everything, but be able to return to the sport of surfing by sitting down and surfing. So those are all activity-specific technologies. So now I'm going to tell you about some environmental technologies. So by environmental, I mean like the ramp outside the building or the automatic door opener, things that are built into the environment to make the environment accessible. So outdoor recreation, that's what our focus is. So we've been working on waterside landings all around the San Francisco Bay. This is one over in Oakland. This is a really super wide ramp. It goes up and down with the tide. This is another one on another site. And then we create this access information about the ramp length and its grade, its range of grade, its typical width. We get the water access route itself, the grades and cross slopes, and the clear spaces that are available. We keep track of, show where the current is, where the fetch is, which is the direction that the wind drives the waves. So we've come up with a way to quantify objectively all the water sites for their accessibility in the San Francisco Bay Area. And the Coastal Conservancy with the state of California is going to use this system for all their water site landings. For trails, we have a different process called the Universal Trail Assessment Process. And we use some simple tools, roll a wheel, smart level, shows us the grade, compass, clinometer, measuring flags. And we go out on the trail and we systematically measure our distance down the trail. We measure the grade using a clinometer to shoot the typical grade. We get the tread width on the trail, very narrow tread width there between those rocks. We get the surface firmness and stability, the mood test sometimes, and I'll show you a more objective way a little bit later on, and the cross slope, the lateral slope that's on the trail. We measure snow trails, hiking trails, horse equestrian trails, ATV trails, OHV trails, all using this process. And we measure the features like the picnic tables and the campfire rings and the grills and all that stuff as well. So we teach people how to do this process. We've certified 1,300 people to do the trail assessment process in the U.S. And we've got trainers all over the country that can teach the training process. And then we've created a high efficiency way to do this. It's sort of like a jogging stroller. It's actually a gun cart that's been converted. We have a sensor box there that measures the grade and cross slope, and a GPS camera and laptop and we roll it down the trail and we measure the conditions along the trail systematically. We have a roller wheel version for narrow trails where you just set it down and you roll it along on the wheel. And then Mike's got his set up on his wheelchair, so his wheelchair is actually measuring the grade across on the trail. He's got the GPS in the back of his chair and the laptop on his lap. This is what the screen looks like. It's designed with high contrast for using the screen outside. We get our, again, measuring live grade and cross-slope and distance, and then capture the tread width, measure that, type that in, and pulls over the data. Now we're working on how to measure all the outdoor recreation features, like the picnic tables and the rings and the grills, all that stuff, and that's going to be kind of an app that you can access with any mobile device that has a web browser. So it's going to access the smart sensor box, which is going to have a Wi-Fi computer inside of it that you're going through the assessment process. And these are all the features that have to be measured for the outdoor recreation process, because these are all the things that there are accessibility standards for each one of these now that have been signed into law as part of the Americans with Disabilities Act. So, like for example, cooking grill, it's got height, a water pump's got to have certain forces for reaching it and pumping the water. So we measure, with the spring gauge what the force is. We measure the height of the handle to make sure the height's in a certain range that people can reach it. We measure the clear space around the table and under the table. And so our app's going to sort of visually guide the person through, this is the measurement to make now, this is the measurement to make now. So we're working on this right now, trying to complete this project. This is an example of our trail signage. It's kind of a food facts label for a trail. We get typical and maximum grade, cross-up, and tread width. We posted on 4x4 signposts and fiberglass impregnated panels. We also make these full panel maps that are like 2 by 3 feet. And we've done we're working on every state park will be finished in Nevada in a couple of years. We've been systematically doing them all. We're working with states that are in the process of doing this in their state. Alabama's working on the trails in there. So one at a time, where these states are kind of coming around, because now it's law. Now it's law. Guidelines say for the trails that you have, you need to get what the conditions are so people can decide what they want. Some people are looking for more steep things, some are looking for flat, some are looking for wide enough. Everybody's looking for a different experience. Mountain bikes, some people are just looking for single track trails. So the idea is that we get the information there so that anybody can make a decision about going there, whether it's a mom with her stroller and kids, or a dad with stroller and kids, or grandparents, or whatever, to be able to get onto the trail. So this is Washoe State Park, just south of Reno, north of Carson City. So we color code the trails, and then we put all the trail access information in the panel. This is Tahoe Meadows up on Woods Highway, part of the Tahoe Rim Trail that goes through here around Lake Tahoe. And we have a website where all the information gets posted, and you can go in and search by trails for specific, like I want trails that are a certain width or a certain grade, and you can see what trails are available in that range. So sidewalks are another issue, another thing that needs to be accessible. So we've been measuring a lot of college campuses. Our company wrote the design guidelines for federal highways for designing sidewalks and trails. And now they're going through a rule-making process with the U.S. Access Board to become standards for all cities. So for trails, you have to have certain grades and certain slopes for certain distances. I'm not going to read all the numbers, but cross slope maximum 5% on a trail, for example. The tread width has to be a certain minimum width, 36 inches for most trails. And then playgrounds. Playgrounds need to be accessible as well. The biggest barrier on a playground for accessibility, though, is the surface. Because if I roll into a shredded rubber playground, I'm going to just sink. And then, because they shred up steel-belted radials, I'll usually get 3 flat tires within about 20 minutes because the little wires sticking out of the rubber puncture my tires. So I want to be able to get out of the playground with my daughter and play. So we've come up with a way to measure the playground for accessibility. We use an instrumented wheel with strain gauges, and we set up the material in a 4 by 12 foot test bed. and we push the chair 4 pushes, and we measure the area under the curve and calculate the work to roll across the playground compared to certain ramp grades. So we can, for any surface, we could say this surface, this one like here, is probably equivalent to about a 2 to 3% ramp grade because it's a commercial industrial carpet. So for each surface, we know about how much work it is to negotiate that surface. So now we've designed a portable device to do that. See, this is a rotational penetrometer. You stand on it, and then it has an indenter, which is an 8-inch wheelchair canister. And so you set it down on the surface, and then you release the spring. It's a precision spring. And there's just a caliper like you'd use in the machine shop right there. And it measures how far the indenter goes into the surface. And then you twist that's your firmness reading. And then you twist the indenter, and if the surface is unstable, it digs in farther. So then you get the stability reading. So there's the, there's the indenter. And you can see how it's twisted, and it gets a 90-degree swish every time you push it back and forth. And then you can see the caliper that you can read. So trails are very often firm, but they're not stable. So you go to turn on them, and then you sink, and then you're stuck. So this is a trail that had a very unstable surface. So we dug it out, and we put in this geopave. It's a plastic structure that's about 1 inch thick. These little plastic circles, and a geo fabric underneath it, and then we filled it up with put the native material right back into the trail, and then you can't even tell it's there, right? So this is how we can stabilize, this is how we stabilized a lot of trail in the Lake Tahoe Basin, because you can't bring in non-native material. So here you can see before the application, pretty firm, 0.2 of an inch, but look at the stability. It's like 0.7 to 0.8 inches of penetration, and then after we stabilize it, we're down to 0.3 or 0.4 inches of penetration. So we can objectively measure how stable it is with that device. So for measuring the sidewalks, we started out using smart levels and stuff, and that's very, very labor intensive, because you've got to measure the grade of the ramp, the flare, the gutter, the street, and the landing. So you're kneeling down many, many, many times. Also the transition heights, which trip people, have to be measured, because anything over 1/4 inch is a tripping hazard. Here you can see a trace of one. This one's over 1/2 inch, 0.56 inches. And so having to trace those with a tracing device is very time consuming. So we designed the sidewalk assessment process using a real rigid base and a wireless wheel. We can quickly measure things. So this is our height device. We just stomp it down, and it measures the height to 1 millimeter on the tripping hazard. We have a data collection software. The software says, put the card here and hit the enter key. So he puts the card there, hits the enter key, and it grabs the grade cross up. So then it says roll up here, and then hit the enter. So basically the software guides you through where to put the cart, how to enter the information. And there we're measuring the gutter grade, which is important. When you go through that gutter from the ramp, you can hit your footrest and get thrown out of your wheelchair really easily. Then we use the wheel to measure off. It's telling it to measure off the width of the panel and the length of the panel. So what we can do is we can take all this data and we put it into a GIS maps. A GIS map gives you a symbol and shows you what's going on. So like this one's showing everything that's green is compliant in the width. Everything that's red isn't wide enough. Or in this case, we're showing how much cross slope there is. So all the red is greater than 5% cross slope. The yellow is 2 to 5%, because it's supposed to be less than 2% cross slope sidewalk. So we can real quickly go out and measure all these different obstacles and obstructions, and then they all get fed right into layers in GIS maps of cities, so that they can see exactly, and they can create reports of the sidewalks that need to be going, go out and grind and whatnot. This is tripping hazards by height. Everything that's yellow is less than 1/2 inch, and the ones that are orange are over 1/2 inch. So I'm going to talk to you a little bit about some of the standards we write. So I mentioned the wheelchair standards for testing wheelchairs. We've also been designing standards for measuring fitness equipment for accessibility. So if we can have a way to assess fitness equipment for accessibility, the Access Board is requiring that 10% of all fitness equipment meet accessibility standards. And so that way, we come up with a way to measure the equipment for accessibility. You can see that the bench on this machine is just a little tiny triangle, and this guy can't really balance on there. Treadmills, if they have too high of a step, people can't step up onto it to do the walking exercise that they need. Or if the handrail, in this case, is this big giant oval, you can't even get your hand around it to safely hold on to the treadmill. So, and if somebody has a visual impairment, they won't see the black pin on the weight stack to adjust the weight. So there need to be high contrast weight adjustments and things like that. So there's thinking about all different disabilities for different users. The shape of the pin needs to be such that somebody without grip can get the pin in and out without fine motor function in their fingers. So for somebody that's visually impaired, certain kinds of display screens might not be very usable. That's in color. Okay, if I'm colorblind, that's in black and white. That's the same image in black and white. But this one is designed with more contrast, and so in black and white, you can actually see the controls. So we have contrast requirements, and our company created a contrast requirement just using a spot meter for a camera, that we could measure the light and dark contrast in signage and buildings and all kinds of things to create control panels and software that has good contrast for people that can't see it. So we've also started writing some standards for people with cognitive impairments want to be able to choose products that they can use, right? If a product is too complex, it might not be very usable. So our goal with the universal design assessment of consumer products is to determine how complex products are. Everything from phones to calendars, fire extinguishers, cameras. And so we're trying to come up with ways to measure things. Like there's cameras that have 4 buttons and there's cameras that have 20 buttons. So there's all different levels of usability of consumer products. And so we just got published a first version of a standard that's objective ways to measure consumer products for their usability in terms of their simplicity versus complexity. I also work on amusement park rides, and we design the accommodations for them. 2 weeks ago, I got to go down and test out the new, Cars, Driving Crazy Car, what's the name of the movie? Fast and Furious. Anybody seen a Fast and Furious movie? Okay, I guess there's 8 of them. I have to admit I haven't seen any of them yet. But the Fast and Furious ride, so on that ride we've designed a way to transfer on and off the ride car, and we've also designed an ADA cartridge that a wheelchair will go on and slide the ADA cartridge, because the ultimate goal is if someone can get in their wheelchair, that makes the ride that much more accessible for someone to get into. Here I'm transferring into Spider-Man because the whole ride vehicle comes up, the top of it comes up so you can transfer in, and then the whole top comes back down. So there's no door to open because the door is way up above and comes back down into place. So Fast and Furious is going to do the same kind of thing. The whole door on this bus, like safari vehicle, comes up and then comes back down to ride the ride. So this one has a transfer device. Part of the side folds in, you transfer to there, and then transfer down into the ride, and then you fold that up and your companion can sit down next to you. So there's all different ways. This is anybody ridden Jurassic Park, the water ride? So this is the old Jurassic Park ride. It's a water ride. It's really low and really hard to get into because you really can only transfer about 6 or 7 inches at a time. So we prototyped this out of wood. So I transfer. So 1, 2, 3 transfers to get down, 3 7-inch transfers to get down in Jurassic Park. And that's the finished product. So now they're using that on the ride. So they just come up and plug that on there. You transfer down into the ride, you pull it off, you ride the ride, you come back to the unload station, transfer back up, 1, 2, 3, back into your wheelchair. So that's the kind of thing. This is anybody heard of Rocket in Orlando? The roller coaster that goes straight up. That's one of the toughest rides I've ever worked on because it's a German designed, just a single thing that comes across your waist, but very hard to get into. So we had to design a transfer vehicle that you transferred onto, and it kind of plugged you into the ride to transfer into the seat. And there's the rocket right there. Takes you straight up and then down. Pretty wild ride. So this was mocking it up. So this is where I get involved. So we're in a warehouse here about 5 years before Rocket opened. And we're like, okay, how am I going to get from there, to the wheelchair? There's the wheelchair, there's the ride. So we mocked up like a little diving board, upside down paint buckets, right? A piece of wood, my wheelchair cushion. I was like, okay, if I had something right here, I could transfer from that to that. So we ended up having to design this transfer board. So here I am. I'm sitting on the transfer device. See, it's like a little diving board that I'm sitting on with a grab rail. So they're going to plug me into the ride there so I can transfer into the ride. So there I am plugged in, transferred into the ride, and then off I go. So now I'm plugged in, ready to rocket off. So our latest focus that we're working on is air travel. Airline travel is a nightmare for people that use assistive technology, scooters, powered wheelchairs, manual wheelchairs. Paralyzed Veterans of America funded us to do a pilot study. Problem number one, the jetways are really super steep. You're looking down, they can be crazy steep because the building, the airport terminals are off the ground really high to let trucks and stuff go underneath. And the flex jets and the commuter jets can be really small. So you got to go down a really steep ramp to get down to the aircraft. So they can be way steeper than 6 degrees. So that's a problem because when you have to turn sideways to go in the plane, you fall over sideways in the boarding chair. So it's a dangerous environment. 12% of everybody has fallen over in the boarding chair, or another 7.5%, or I have the number there. Another 7% have fallen out of the boarding chair. So you have a 1 in 5 chance of falling over, getting onto an aircraft just in the boarding device. So the boarding devices are not so nice. They're basically like a dolly on wheels. You're supposed to get on this device that's really narrow and roll you into the aircraft. And it's so narrow that when they turn it sideways in the jetway, that's why they fall over. So that's a problem. This is what one of those boarding devices looks like with one of our test subjects. It's such a tiny little thing, and you can see this guy's 300 pounds. He doesn't even fit on the boarding device. He won't even fly anymore. He's been dropped 3 times. So we're looking at the specifications of a boarding device, trying to figure out what should be the specifications of a boarding device to work, because they're dangerous. So here I am transferring into a boarding device. And so my own personal solution is I have these extra wheels underneath my wheelchair. I pull off my wheels, I'm a boarding device. So I roll into the plane, I get down to the jetway, I pull my wheel off, I pull the other wheel off. Now I'm a boarding device, I pull myself, there's my little wheels down there. I pull myself over the plane and I get in. So we're working on things like you open the overheads, put a track up there, and have a battery-powered lift to try to get somebody in the aircraft seat. I can transfer, but a lot of people can't transfer. So we tested all these different transfer devices. This is a miniature overhead gantry. It can actually roll down the aisle and then roll sideways over the aircraft seat. The frame adjusts to the length of the seat, roll the person over sideways, and set them down in the aircraft seat. So this is the kind of technology that's coming along. Also, there's a problem with the sitting pressures. These boarding seats have really firm, shall we say, seats. That's the pressure of me sitting on the boarding device. Red, tailbone, 2 ischial tuberosities. That's a dangerous seat to be sitting on for any length of time. This is my seating in my wheelchair right now. I have a bit of obliquity. It's my left trochanter, and my 2 ischial tuberosities are my legs coming forward this way. That's sitting on the aircraft seat without a cushion. So aircraft seats aren't designed to be comfortable. You've noticed that flying, right? They're designed to pass a crash test. That's why they're not comfortable. Because if you submarine into that cushion, you could slip out under the seatbelt. So there, this is me trying to sit on my cushion on the aircraft seat, and you can see I'm sitting higher, so the headrest is on my shoulders. My feet are off the ground dangling. My legs swell because my feet are dangling. Their blood flow is not happening through my legs. So this is what I do. I put my backpack down as a foot support. I have my seat cushion for my wheelchair. I carry an inflatable REI pillow as a back support. I have this spine support that I've designed. I use one of those neck pillows, and I can put something on the armrest. So when I put all that stuff on there, I can sit comfortably in the airline seat. So I've got a backpack full of stuff that I carry with me on the airplane to be comfortable just to sit. So we need to really educate consumers. Lack of bathrooms on the aircraft is a problem. There's no accessible bathroom on the aircraft. There's 3 skinny, tiny bathrooms. So if we could just get the airline to have 1 accessible bathroom. We surveyed lots and lots of people. No one would fly more than 2 to 3 hours without access to a bathroom. So my only solution is I can go on short hops, like connecting flights. Can't take the nonstop from San Francisco to Washington, D.C. I got to connect somewhere if I need to get off, go to a bathroom, and then get on another flight to get the rest of the flight because I can't get to the bathroom. I've estimated that to eliminate 1 row of seats on one side of the aircraft would be 2% of the ticket cost. So if everybody was willing to pay 2% more, we could have a single accessible bathroom on the aircraft. And 9 of 14 persons knew somebody that needed assistance in a bathroom, and 14 out of 15 said they would pay more for having 1 larger bathroom on the aircraft. Because some people are so tall they can't close the door and sit in the bathroom because it's so short. So that's a problem. So, and my last solution or problem is the narrowness of the aisle. If the aircraft aisle could be fixed, like say they shouldn't be narrower than 18 inches, then we could make the boarding chairs a little wider and they wouldn't fall over. And finally, powered wheelchairs are being damaged badly. This is lifting a powered wheelchair up onto the belt that runs the baggage up into the aircraft. You see the wheelchair is tilted on its side. There's the joystick up by the jet engine, and there's the wheels. So that's how they have to get them in, because they're long and tall, and the doors are wide but not very tall. So some of the chairs have to be tipped, and this is what's happening. There's a broken armrest, there's a broken fender, there's a broken electrical cable, there's a entire wheel broken off the chair. So we're creating standards for designing transportable powered wheelchairs. And we have the airlines, the disability groups, the wheelchair manufacturers participating. We just started these committee meetings in November, and we're working on trying to design a chair so that, like, there's an information card that tells about the chair, that there's an indication of where to turn the power on and off, what the weight of the chair is, where to lift the chair safely to load it, how to disengage the drive motors so it can be pushed, training people to work with the chair, getting on and off the aircraft, making sure the chair has a transit option with the tie downs, like it has for a bus, so that you can secure it in the aircraft, making it so all the components are removable, so you can take the joystick off and actually take that into the aircrafts, because that's the most commonly damaged thing on the wheelchair. And then having a foldable back support. So foldable back support would be the backrest comes off, the leg rests come off, and then the back can fold forward. So this is already exists for some chairs to get them into vans. So this is rolling one into a van. So if the chair had that and had a way to protect the joystick, this is a way to temporarily use Tupperware to protect the joystick, or a way to strap the chair folded in a shut position for a manual chair to keep it from being damaged. And chairs don't get damaged. So it's my daughter and I out in La Ferry, San Francisco. So I have used up almost all of my time except for a few minutes for questions. So.
Let me ask you a question.
Yeah,
I know you've seen a lot of stuff that you've created over the years with all your staff and stuff. So how successful have you been in manufacturing and commercializing this stuff?
So almost every one of our projects has been implemented in some way. Some of the things we've created are books, so they've been published. Some of them have been procedures, so they've become standards. Mostly we found that we were more successful by licensing, like the back support on my chair is licensed, the flex rims are licensed, the hip grip is licensed, because we're not a seating manufacturer for wheelchairs, so we've kind of put things out there. All of our high-risk products, like the monoski and the canoe seat, anytime we design a high-risk product, we just put it in the public domain so that it becomes widely available, because we don't want to accept a royalty or a license on something that has a high risk of injury that's being manufactured by small family-owned businesses that don't have product liability insurance. So the fact that we put the monoski in the public domain 2 years after that world championship, at the next world championship, every monoski in the world had a shock absorber in it. So some of the things that we've just put in the public domain were just kind of the right thing to do, and the White House actually invited me to the Olympics when they found out about that, to go to the Vancouver Olympics. So each device, we sort of decide what's the most successful way to actually commercialize that technology. The rotational penetrometer, we are manufacturing that device and distributing it. The trail assessment equipment, we sell and train people how to use that equipment. The sidewalk assessment process, we have people that are trained that go all over the U.S. to measure sidewalks. We've measured 100 miles in Texas. We've measured 250 miles of sidewalk in New York and Manhattan. So that's a service that we provide. The amusement park stuff that we do is a service. So virtually almost every one of the things that we've either designed or has been implemented in some way as a product, or by licensing or commercializing or putting in the public domain. Piano pedal pushers on our website, so people can just make it. So it's a good question. Thank you.
That's great. We've run out of time, so if you need to leave, this is your time. If you want to come up and talk to Peter personally, great.
We have an internship application on our website if anybody's interested in coming doing stuff with us.
In beautiful Minden, Nevada.
Yeah.